Hello students, let's solve the specimen paper for paper 2 2025, the SL. All right, let's look at the first question. A block of mass 45 kilograms is placed on a horizontal table. There is no friction between the block and the table. An object of mass 15 kilograms is placed on top of the block. A force F acts on the block so that it accelerates. The acceleration of the block, the acceleration of the object, and the acceleration of the block are the same, so they do not move relative to each other. The coefficient of static friction between the block and the object is given to be 0.60. First question is state the nature and direction of the force that accelerates the 15 kilogram object. So if you look here, the force is acting on this 15 kilogram object. It's gravity pulling it down. You also have force normal that's pushing it up. And what's the force that's causing it to move to the right with the 45 kilogram object? Of course, it's the force of friction. So force of friction is responsible for this 15 kilogram object to move with the 45 kilogram object. Right, let's move on to the second part. Determine the largest magnitude of F for which the block and the object do not move relative to each other. So what's the maximum amount of force I can apply such that this block is going to move with the 45 kilogram object? So in order to solve that, we must realize whenever we apply a force strong enough that this object is on the verge of slipping, the force of friction acting on the 15 kilogram object will be given by the equation force of friction equals mu times force normal. All right, this would be mu times mu is given to us. It's 0.6 times force normal is m times g. So that's the force of friction that is acting on this 15 kilogram object. So what would be its acceleration? Acceleration would be the same force that we found here. We need to divide it by the mass of the 15 kilogram object. So we do 0.6 times 15 times 9.8 divided by 15. 15 and 15 goes away. If we solve this, we'll get 0.6 times 9.8, which turns out to be, um, let's plug this thing into our calculator. 0.6 times 9.8. That is 5.88. So that's the acceleration of this 15 kilogram block. Since it's moving with the 45 kilogram block, both of these two blocks will move with the same acceleration. So now if we focus on this entire system, we can write Newton's second law, which is the total force acting on the system equals the mass of the system, that's 60 kilograms, times the acceleration, which is 5.88. If we plug this into a calculator, we get a value of 352.8. But note that we only have two significant figures, so I'm going to truncate this to two significant figures. So the answer to our question would be 350 newtons. And that solves the second part of the problem, 350 newtons. Okay, let's move on to the second question. The second question says, in a microwave oven, electromagnetic waves are emitted so that a standing wave pattern is formed inside the oven. A flat piece of chocolate is placed inside the oven and the microwaves are switched on. The chocolate is stationary. Melted spots form on the chocolate. The diagram shows the pattern of melting on the chocolate. Each square has a length of 1 centimeter. So this is a bar of chocolate and it appears to melt at these particular locations. Outline how this standing wave pattern of melted spots is formed. So the question is, how are standing waves formed in the first place? How does that happen? So we have a source that emits a wave, that wave goes, it reflects from the edge, from the end, from the wall of the oven. and that reflected wave travels back. So we have an incoming wave and we have a reflected wave. These two waves interfere and we get a standing wave pattern. That answers this part of the problem. The part B says find using appropriate measurements from the diagram the frequency of the electromagnetic waves in the oven. So we have to use this diagram and find the frequency of the oven. The important thing to realize is that these spots are the places of the antinodes. So we draw a standing wave pattern that has an antinode here, an antinode here, and an antinode here. So it would look like this. So this would be our wavelength, this distance. So how many boxes is that? It's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 boxes. That means 12 centimeters. So the lambda wavelength is about 12 centimeters. How would we find the frequency? We use the equation V equals lambda F. But what's V? Since this is an electromagnetic wave, it travels with the speed of light. So V is equal to C, that's equal to lambda F. All we have to do is to substitute the values of C and convert centimeters to meters, and you're going to get the value of frequency. All right, let's move on to the third problem. A satellite moves around Earth in a circular orbit. Draw an arrow on the diagram to represent the direction of the acceleration of the satellite. So we have to show the direction of satellite. Well, the only force that acts on the satellite is due to gravity, and that points vertically down. If that's the force, that has to be the direction of acceleration. That solves the first part of the problem. Moving on to part B, the following data are given. We are given the mass of Earth, the radius of Earth, and the orbital period of the satellite. The question says Kepler's third law of motion states that the time it takes for one complete trip in its orbit is equal to kr cube, where r is the radius of its orbit. We have to show that k equals 4 pi square over gm. In order to solve this problem, you'll see that in your data booklet, we have the orbital speed given as square root gm over the radius. All right. So what's the speed? I can re I can rewrite the speed as total distance traveled. That's 2 pi r divided by the time period. So I have 2 pi r equals square root gm over r. Okay. Let's square both sides of the equation. We get 2 pi r square. If I square this, the square root will go away. Okay. So let's simplify this expression. I get 4 pi r square over t square equals gm over r. Okay, so let's rearrange this equation. I'll get this implies t square over 4 pi r square equals r over gm. This means that t square equals 4 pi r cube over gm. Okay, let's box this equation. And now we can clearly see that this k here is in fact 4 pi. We have a square here. I just forgot a square. We have a square here. We just proved that t square equals kr cube, where k is this term. And that proves this question. Determine the height of the satellite above the Earth's surface. Okay, so we want to find how high it is from the surface of Earth. Here you have to be careful. If this is Earth, this is our Earth, and this is the satellite, this is the radius of the orbit. We need to subtract the radius of the Earth to find this height. Okay, to find the height, you simply do radius of the orbit minus radius of Earth. How would you find the radius of the orbit? You can simply use this equation. T is given, you plug it here. M is given, you plug it here. R is given, you plug it. Oh, so read, yeah, T is given, you just plug it here. M is given, you plug it here and you solve for R. Once you have that R, that goes here. Then you subtract the radius of Earth and you get the height above the surface of Earth, right? You should not waste time with that. You'll be able to do that. It's just plugging the values into the equation. Let's move to the fourth question. A smoke detector uses the radioactive nuclide americium-241. It's contained in a chamber that is open to the air. There are two electrodes in the chamber. So we have this of a cathode and an anode. So this 241 element emits alpha particles. So when it emits alpha particle, it's going to ionize the air inside the chamber. So we get a positive ion and an electron. This is called an ion pair. Okay, that's good. And these electrons and positive ions, they travel towards the electrodes. When they travel towards the electrodes, we get current. We are also given the length of this distance between the two electrodes. The question says, let me clear this. And this has 241 nucleons and 146 neutrons, and it decays to neptunium through alpha emission. We have to complete this decay reaction. So how do we do this? It has 241, that means it has 241 nucleons and it has 146 neutrons. So how do we find the proton number? We do 241 minus 146, that's 95 protons. When it decays, we know alpha particle has 2 protons and 4 nucleons. So how many protons remain? We would do 95 minus 2, that's 93. And we would do 241 minus 4. That will give us the nucleon number. 241 minus 4, that gives us 237. So that solves this problem. Okay, let's move on. Outline why the radioactive source is safe for use in a house. Problem here is we're using a radioactive material that's emitting alpha particles. How come this is safe to use in our homes? The answer is that alpha particles have a very small penetration power. So they travel a couple of centimeters in the air and stop. So this, therefore, is safe. Okay, this question is a bit tricky, so we need to be careful. The initial activity of the source is 42 kilobecquerel. 33% of alpha particles emitted are used to form the ion pair. Each alpha particle has this amount of energy, and we need 15 electron volts to get one ion pair. We have to find the maximum current in the chamber if there is no smoke. So how do we do this? Well, we know there are 42 kilobecquerel, that means 42,000 alpha particles produced every second. After those, 33% are of use. 33% of alpha particles will actually lead to ion production. That's one third of the number. And how much energy will these alpha particles have? Well, each alpha particle has 5 mega electron volts. So I multiply the number of alpha particles with the energy in one alpha particle. Now, this is the total energy that we have that's going to produce the ion pair. How many ion pairs are going to be produced? Well, we need to divide this energy with the energy required to produce one ion pair. So this is the amount of ions that are going to be produced every second. How do we find the charge? We simply multiply it by the charge, elementary charge on each proton. So if you compute this number, you're going to get the number of ions produced every second. Once those ions are produced, they're going to be swept away in that very second to the ends of those electrodes, giving us the current. So this, in fact, gives us the value of current that is produced. Okay, let's move on to the next question. We have a star, a main sequence star, whose radiation curve is shown here. We have to show that the surface temperature is about 9,000 Kelvin. So what do? We use this equation, peak wavelength times temperature. It's a constant, okay? You'll find this constant in your data booklet. If you crack open a data booklet, it is given, uh, check this again. The constant is given here, 2.9 into 10 to the minus 3. So that's what we are going to use here. Lambda max times T equals this constant. How do I find lambda max? Well, we simply read it off from here. This is the peak wavelength, 0.3 into 10 to the minus 6. So that goes here, 0.6 into 10 to the minus 6 times the Kelvin temperature is a fixed constant. The value of the constant is here, 2.9 into 10 to the minus 3. So let's use that. 2.9 into 10 to the minus 3. And now you just need to solve for t. T would be 2.9 into 10 to the minus 3. Yeah, we'll do double slit diffraction. Once I finish this paper, then I'll go through that, all right? So we do 2.9 into 10 to the minus 3 divided by 0.6 into 10 to the minus 6, all right? So if you compute this number, it's going to turn around close to 9,000 Kelvin. All right. Let's push on to the second part of the problem. The apparent brightness is given to us, and its distance is given. We have to estimate the radius. How do we do this? So if this is the star, let's say this is our star. It has a certain radius, and it's at a distance of d from our Earth. All right. Now, what's the formula for brightness? Brightness is given as luminosity divided by 4 pi d square, where d is this distance. All right, this brightness thing, it's given to us. But what about luminosity? What's the equation for luminosity? Luminosity is sigma, the surface area, and temperature to the 4. What's the surface area of a star? Well, it's a spherical object, so its surface area is going to be 4 pi r square t to the 4. I can grab this and plug it here. All right, so our equation would become B equals sigma 4 pi r square t to the 4 over 4 pi t square. 4 pi goes away, and we are trying to solve for r, so let's make r our subject. We get bd square over sigma t to the 4 with a square root. That's our r. All the values are given to us. We know b, can plug it here. We know d, can plug it here. This is a constant. T we already found out. So we just need to plug and chug. All right, no need to waste time on that. That's how we do this. And the radius of the sun is about 7 into 10 to the 5 kilometers. So we have to draw on this HR diagram the position of our star. Now, if we look at the mark scheme, if we do the calculations for our previous step, we will find that the distance is about 1.4 gigameters. That is twice the distance of our sun. About, so the radius of this of our star, it's about. Why do we use 4 pi r square? Yes, it's the surface area of the star. It's a sphere. We consider it to be a sphere. Does that make sense? Yeah. So the radius of the star is about 2 times the radius of the sun. So we have to draw the position of our star. So where would it be? It would lie between this line and this line. These are lines of constant stellar radii. So our radius is about 2 times R and its temperature is 9,000 Kelvin. Keep in mind that temperature on an HR diagram, it doesn't increase this way. No, it goes this way. It increases from right to left. Since our temperature was about 9,000 Kelvin, so it's somewhere here, and the radius lies closer to 1. So we draw it somewhere here. All right, makes sense? All right, let's try question 6. Let me clear this. So we have small pieces of solid paraffin with a total mass of 30 gram at temperature 42 degrees Celsius are mixed with a liquid paraffin at temperature 240 degrees Celsius. The mixture is stirred until an equilibrium temperature is reached. The following data is given. So we have this data. What's the question? Calculate the equilibrium temperature of the mixture. So we have a liquid container that contains it has a liquid paraffin at temperature 240 degrees Celsius. And we mix in some solid paraffin blocks in it. And what's going to happen? The solid paraffin blocks are going to heat up. We're going to get an equilibrium temperature T. All right. So how much heat, the amount of heat lost by the fluid is going to be gained by the solid blocks. So how much heat will they gain? Well, the first step, what's going to happen is that these solid blocks will go from 42 degrees Celsius to 47 degrees Celsius. They have to reach the melting point first. So what's the heat they're going to use? We use the mass of the solid paraffin blocks. I'll write that MS, heat capacity of the solid paraffin times the temperature change, which is 5. So this is for heating. What happens after they reach the melting point? Now they're going to melt. How much time, how much energy how much energy are they going to take to melt? It's the latent heat. So that would be mass of the solid paraffin times the latent heat of fusion. All right. So now these paraffin blocks have melted. What now? Now they are going to heat up to the equilibrium temperature. So we'll use mass of paraffin blocks. Now we need to use heat capacity of the liquid times the temperature change. That would be T minus 47. Right? 47 is the temperature when it melts, then it goes up in temperature and reaches temperature T. So this is the story for these solid blocks. Where do they get this energy from? They get this energy from the liquid. So this amount of heat must have been lost by the liquid. So the liquid simply falls in temperature. It goes from temperature 240 degrees to temperature T. So let's write that equation. The amount of heat lost by the liquid paraffin would be mass of liquid, all right, mass of liquid, heat capacity of liquid paraffin times the temperature drop. That is 240 minus T. So this is the amount of heat lost by the liquid paraffin. It must be equal to this entire term. Okay, so you need to equate these two. It's a messy equation and you need to solve for T. That's going to give you the equilibrium temperature. If you check the mark scheme, that's exactly what they have done. All right, you need to plug this in and do the manual work there. Okay, let's move on to the next part of the question. When the experiment was carried out, the equilibrium temperature of the mixture was found to be different from the theoretical value. What's the reason for this? The reason is in our calculations, we assume that the liquid paraffin, whatever heat it loses, is going to go entirely into the solid paraffin blocks. That's not entirely true. Some of the heat is lost. So that's why we are going to get a different value from the theoretical value. Okay, question 7. The diagram shows two parallel conducting plates We have a positively charged one. We have a negatively charged one. Draw the electric field lines due to the charged plates. What do? We simply draw electric field lines as arrows pointing downwards. But keep in mind that these distances between these arrows, they should be consistent. It's a uniform field, so those distances are the same. And you may also show these fringe effects. That solves this part of the problem. Let's move on to part B. We are given the potential difference and we are given the distance between them. We are supposed to find the electric field strength. So what do? We use electric field strength is the potential difference divided by the separation. So you need to plug in 960 over here, 8 into 10 to the minus 3. You need to convert it into meters. That's going to give you the electric field. Okay, let's move on. So what happens is they drop an oil drop into this, and this oil drop becomes charged. Why does that happen? What happens is as this oil drop falls, it hits against the air. So we have, air is surrounding, is filled inside the tube. When the oil drop falls through it, it's going to hit against those atoms of the air molecules. Those air molecules can either supply electrons to the oil drop or take away electrons from the oil drop. That's what's going to make this oil drop charged. All right. Another way you can say is that there is going to be friction. There's going to be friction between this oil drop and the layers of air between them. It's the same thing. You have a rod and you begin to rub it, you might knock off electrons from the rod. It's the same thing going here. It's the same reasoning here. That's how this oil drop becomes charged. Okay, let's press on. The oil drop is observed to be stationary in the space between the plates. That means this oil drop is just hanging there. Buoyancy is one of the forces acting on the drop. The density of oil is 730 times that of air. So the buoyancy force is much smaller than the weight. So if this is our oil drop, these are the two plates, positive and negative. This is our electric field. This is the oil drop. Uh, this is our oil drop. It has two forces acting on it. The force of gravity pulling it down and the force of buoyancy that is pushing it back up. All right, how do we find the force of gravity? Force of gravity simply would be mass of the object times g. We can replace mass by density of oil times its volume times g. So this is gravitational force. How do we find the buoyant force? For that, you can look up to your data booklet. It's real quick. Scroll to the equation. Where is the equation? It is density times volume times b. All right, I don't want to waste your time. Trust me, you'll find it. It's density of the fluid, volume times g. Okay, what's the fluid here? It's density of air. So this is the buoyant force. But where's the catch? The catch is density of oil is 730 times greater than that of air. That means density of oil is 730 times the density of air. So I'll plug this value here. What do I get? I get the force of gravity is 730 density of air Vg. Now we can compare this equation with this equation. What do you note? We note that the density, that the force of gravity is 730 times the force of buoyancy. That means this buoyancy force is much smaller than the weight, hence proving this assumption. Draw the forces acting on the oil drop, ignoring the buoyancy force. So if the buoyancy force is negligible, how come this oil drop is stationary? How come it's hanging in air? The gravity is pulling it down. Buoyancy force is negligible. How come it's stationary? The reason behind that is there's an electric force that is pushing this charge upwards. So this is force gravity, this is force electric, and they have to be equal in magnitude. You need to draw them equal in length. Okay, that solves this part of the problem. Let's press on. Show that the electric charge is given by this equation. We need to show this is the charge present on the oil drop. So what do we do since this is stationary? I'm going to say electric force equals gravitational force, all right? But what's the equation for electric force? It's Q, that's the charge, on the oil drop times the electric field. Electric field gives us the force on a unit charge. It's force per coulomb. Since we have Q coulombs, the force is going to be QE. So QE equals force of gravity. But what's force of gravity? It's density of oil, G times V. Okay, so yeah, that's it. So if I rearrange this equation, I get Q equals rho G V over E. And this is the equation we had to prove here. All right, let's move on. State the sign of the charge on the oil drop. Is this oil drop positively charged or negatively charged? Well, if it has to stay in air, there must be a force pushing it upwards. Since there's a positive plate on top, this must be a negative charge such that it feels the force of attraction. So this has to be negatively charged. Okay, great. Now let's move on. The electric field is turned off. Okay, so there's no electric field now. The oil drop begins to fall downwards with a constant speed v. We have to show why the force is given, why this equation holds. What happens is if the oil drops falls vertically and it falls with a constant speed. Constant speed once again means there has to be no net force. So the force now acting on the oil drop is the force of drag. Drag force is pushing it up. That is simply the resistance force, resistance from the air. That resistive force must be balanced by the gravitational force. But what is the resistive force? It's given by the Stokes law, which is 6 pi eta, radius of the sphere, times the speed with which it's falling. This has to equal force of gravity, which is density of object, g, v. So these two equations have to be equal to one another. 6 pi eta rv equals rho 0 g v. And that solves this part of the problem. We are given r, we are given eta, we are given v. You can take these three and plug it here. This we already knew. And we have to find the charge. Oh, so we know r, eta, and v, we have to find the charge. So we can use our previous equation that is here. We know E, we know rho 0 GV, it's the force of gravity, it's equal to 6 pi eta RV. So I can write Q equals 6 pi eta RV over E. These three values are given below. Electric field we found already. So you can plug them here and we can solve for Q. Okay, this part is interesting. The oil drop splits into two parts of equal mass. Both are charged. What is the charge on each part? So if this is our oil drop, all right, we found its charge. The charge turns out to be 4.79 into 10 to the minus 19 coulomb. What I do is I split it into two parts, two equal parts. How much charge will be on this side and how much charge will be on this side. Before I do that, let's divide it by the charge on an electron. This will give me how many electrons are present on this sphere. This turns out to be 3. So there are 3 electrons present on this sphere. So once I split it into two parts, I'm not going to get 1.5 electron and 1.5 electron. That doesn't happen. You'll get two electrons on one side and one electron on the other side. So the ratio is 2:1. Okay, 1e and 2e. And that completes that. Oh, that completes the entire specimen paper. All right. Is there anything that you guys need help with? You can drop it in the comments and I'll try and help you out. I think we had double slit diffraction. So let's crack open our data booklet to go over double slit diffraction real quick. You'll find the relevant equations here. Let's clear this out. So in a double slit diffraction, we have two slits separated by some distance, and you have a screen over here. So what happens is light from these two ends, it goes on and forms an interference pattern. Whenever these two rays are interact and we have a constructive interference, you'll see a bright spot. Whenever they interfere and they are out of phase, we'll see a dark spot. So this pattern keeps on repeating: bright spot, dark spot, bright spot, dark spot. The rule is that whenever the whenever the path differences between these two rays is an integer multiple of lambda. If the path difference is 1 lambda, 2 lambda, 3 lambda, or 4 lambda, or any integer lambda, you're going to get constructive interference. Constructive interference means a bright spot. That's over here. And whenever the two light rays meet such that the path difference is either half a lambda, 3 half a lambda, 5 half a lambda, you're going to get destructive interference. So that means you're going to get a dark spot. That's what these two equations mean. This equation over here, this is for single slit diffraction. So we have a single opening and you have a screen. What's the pattern that you're going to see? You're going to see a bright spot at the center and then tiny little peaks above and below the central maxima. This angle over here, the angle of the first minima, this is theta. It's given by this equation. Lambda, the wavelength, b is this slit width. All right. So this is the equation to find the angle for the first destructive interference. You need to keep in mind for single slit interference, there is no equation for constructive interference. We only have one equation, and that's for destructive interference. What about this one? This one is for a diffraction grating. What's a diffraction grating? It's literally multiple holes in a slit, like we have multiple slits, and this equation is going to give you the interference, the constructive interference, the places you're going to see bright spots. So what's d in this equation? D is this separation. Thermodynamics questions. Okay, let's try one thermodynamics question. Let's finish this and then move on to thermodynamics. Where d is this slit separation and sine theta is the angle where you get the bright spots. Are you in HL, your local tutor? Are you in HL or are you in SL? Okay, I'm not sure if you're in HL or SL, but I can still anyway guide you with the data booklet on how to approach thermodynamic problems. Yeah, so the equations that we have for thermodynamics are given here. This one is a law of thermodynamics. It says that the change in internal energy is the total energy of a gas. You can increase it if you supply more heat, that's Q, and you're going to get a decrease in the internal energy if the gas does work. Okay, that's why we have a minus, right? And then we have this equation, work equals P del V. This equation tells us if you have a pressure versus volume graph, all right? Let's say the graph looks like this. This is pressure, this is volume, and you're supposed to find how much work is being done by the gas. All you have to do is you have to find this area under the pressure volume graph. That's going to give you the work done by the gas, all right? What's this equation about? Whenever you whenever a gas changes its temperature, you can find how much internal energy change has occurred in the gas. All you have to do is 3 over 2 n, the number of moles, or is the gas constant, times the change in temperature. This means that for an isothermal process, if you have an isothermal process, delta T is going to be 0, since it doesn't have any change in the temperature. If delta T is 0, delta U is going to be 0. If delta U is 0, this term goes away. We get Q equals W. That means the amount of heat you supply is equal to the amount of work done by the gas in an isothermal process. All right. This equation relates the entropy of a system. If you supply heat to a system, delta Q is positive. If you take away heat from a system, delta Q is negative, meaning if you supply heat to a system, its entropy is going to increase. Take out heat from it, entropy is going to decrease. And then we have this equation. IB loves to use questions based on this particular equation. This equation is only used for an adiabatic process. What's an adiabatic process? Adiabatic process is a process in which no heat is either taken away from a gas or being given to a gas. There's no heat exchange. Okay, so if there's no heat exchange, that process is adiabatic, and then you can use this equation. PV to the 5 over 3 is a constant. That means between two processes, you can use P1, V1, 5 over 3 equals P2, V2, 5 over 3. So if you know P1, V1, and P2, you can find V2 using this equation. But this, once again, is only used in an adiabatic process. Finally, I would say this equation is important. This gives you the maximum efficiency of a heat engine. If the question says, I have a heat source at this temperature and another heat sink at this temperature, what's the maximum efficiency you can have? What's the maximum possible efficiency? The equation you would use is 1 minus the temperature of the cold sink minus the temperature of the hot source. That's going to give the maximum theoretical possible efficiency. All right, I think, is there anything else you need help with? Anybody, or um, I think that's it, right? How did your paper one go? Everybody is saying that the paper was really difficult. Is that true? All right, guys, I think let's wrap it up here. Go through a data booklet. Once again, there are many videos on YouTube that go through the data booklet. I would suggest you to do the same. All the best for your exam. All right. I'll see you then. Take care. Bye.